And yep, thank you. Our next talk is efficient parameterized algorithms for data packing by lots of people. And is it Amir that's giving the talk? Yes. Amir Gohashed. Can you pronounce it for us?
Yes, sure. Amir Goharshadi.
Thank you. We'll be giving the talk.
This is joint work with Krishnendu Chatterjee, Nastaran Okati, and Andreas Pavlogiannis. So let me first start by giving you an overview of what we're going to do in this work. So we are considering the problem of data packing. I will define this problem a little bit later, but what I need to say now is that it's a classical problem in cache management, and it is known to be both NP-hard and hard to approximate within any non-trivial factor. So what happens in the real world is that people use heuristics, and the problem is that these heuristics have no theoretical guarantees. So what we did in this work is that we tried to find theoretical algorithmic results for data packing, and the way we do it is that we first reduce data packing to a problem over graphs, and then we show that this problem can be solved in linear time if the graphs have some nice structural property, basically if they have constant trivets. And finally, we experimentally show that graphs that are obtained from programs that are common and are used in everyday world actually have these nice properties. So our main contribution is that we provide the first positive theoretical results for the problem of data packing. So let me start by telling you about the setting of the problem. Assume that we have a two-level memory system where we have a large but slow main memory and a small but fast cache. This is nothing new. And then we assume that the cache can hold up to m pages or blocks, and that each block can hold up to p different data items. And when a program wants to access a data item, if the block containing that data item is not already in the cache, we have to copy it from the main memory to the cache, and this is called the cache miss, and it takes a lot of time. So what we want to do is to minimize the number of cache misses. And we are looking at the offline version of this problem because the offline version is already too hard. And so we assume that we are given a sequence R of accesses to the data items, and our goal is to minimize the number of cache misses over this sequence R. And just as a matter of notation, I use big N to denote the length of the sequence and small n to denote the number of distinct data items. So the first thing that we realize is that minimizing cache misses can actually be divided into two different parts, two different problems. One is paging, which is basically deciding which page or which block you're going to kick out from the cache when you need to copy a new block into the cache. And the second one is data packing, which is choosing a data placement scheme, choosing which data items to put together in the same block. Remember that we can only put at most p data items in the same block. And the focus of our work is on data packing. So I'm going to define the notion of access graph, and I do it by an example. Suppose that we have a sequence of accesses to data items. We just create a graph where each data item corresponds to a vertex, and we put an edge between two vertices if their corresponding data items appear right after each other. So for example, here, there is an edge from A to B because AB appears here. And of course, we can give weights to the edges of this graph, which shows the number of times that these elements appeared right after each other. So the weight of the edge BD is 3 because here we have BD and then again DB and BD. So there are 3 times. So this is the concept of access graph. And we can also define some extension of this, which is called access hypergraph. A hypergraph is basically a graph in which each edge can connect more than one vertex. And when we want to create an access hypergraph of, say, order 3 of this access sequence, what we do is that we start at every access point, And we go back until we see 3 different data items, and then we put an edge between everything that we saw. So this is an edge, and if we start from this D, it takes up until this A to see 3 different items, so this is another edge. So what we want to do is to look at these access graphs and access hypergraphs and somehow exploit their structural properties for finding better algorithms for data packing. So the structural property that we want to look at is a classical graph property called tree-widths, and I'm not going to go into it in much detail, but the way I like to define it is using nice tree decompositions. So suppose that we have a graph G, like the graph we have up here, and we want to decompose this graph such that we create it in small increments. So a nice tree decomposition of this graph is basically a tree, and it's a rooted tree. Here, my root is the node on the left. And the way it works is that I start from an empty graph in the leaves, and at each step I can make a very small change, either adding a new vertex or adding edges between vertices, stuff like that, until I get to the main graph. And at each step I also have a set of active vertices, which are shown in red, and a set of deactivated vertices, which are shown in blue. And I can only change stuff in relation to the active vertices. So for example, I can add an edge between 2 active vertices, or I can forget an active vertex to make it deactivated, so on. And another thing that I can do is that if there are 2 different subgraphs that I've made and they have the same set of active vertices but have nothing else in common, I can just merge them and join them into a bigger graph. So this is called a nice tree decomposition of that graph, and the width of this tree decomposition is the maximum number of active vertices minus 1. Minus 1 is for historical reasons, and I don't want to get into it, but so the width of this tree decomposition is actually 2 because we have at most 3 active vertices, and the tree width of a graph is the smallest width among all of its tree decompositions. And a well-known theorem is that if a graph has constant tree widths, then in linear time you can find a nice tree decomposition of the graph, something like this. Now, so I'm now going to get into the main problem of data packing. The previous result that existed was that for any non-trivial packing factors and cache sizes, data packing is firstly NP-hard, and secondly, unless P equals NP, you cannot approximate data packing within any non-trivial factor. So you cannot approximate it within a factor of n to the power of 1 minus epsilon for any epsilon, and n is the length of the sequence. So approximating with a factor of n is just completely trivial. And this result was actually published in PubL 2016 by Lavai. And these are our results. So the yellow parts are the same results that I just told you, the previous results. On the x-axis, we have the cache size m. And on the y-axis, we have the degree of the hypergraph that we're assuming has constant tree widths. So for cache size 1, we know that it's NP-hard in general. But in this paper, we show that if the access graph or access hypergraph of order 2 has constant tree widths, then we can solve the problem in linear time. And we can also extend this result to larger cache sizes, but we need constant tree widths for hypergraphs of order m-1 p plus 2. And we also show that this result is tight in the sense that having constant tree widths on any lower order is not enough and the problem remains NP-hard. We also get a new hardness of approximation result. So right now in this talk, I don't have time to go into all of these. So I just took the simplest one, this blue part, the linear time algorithm for when the cache has unit size. And I'm going to present this, and the other algorithm, the green part, is very similar, but a little bit more technical. You can see the paper for that. So the first thing that I do is that I say, okay, when you're looking for a partitioning of data items into blocks, you can actually think of it as a partitioning of your graph of your graph vertices into sets of size at most p. Here, let's say p is 2. And then you can think of this sequence of accesses to data items as a walk on this graph. And it's a walk that, for example, goes through this edge 3 times. Now, if we make this assumption, then when does a cache miss occur? Note that our cache has size 1 here, so a cache miss occurs anytime you go from one partition to another partition. So I define this notion of cross edge, and I say that an edge that goes from one partition to another one is a cross edge, and data packing is effectively reduced to finding a partitioning of vertices that minimizes the total weight of cross edges. And to find this using our tree decomposition, I define the notion of states. And basically, the way I do this is that I say, let's say that A is a subset of vertices. A state over A is a way of partitioning the vertices of A into sets of size at most P. But it also has a second component, and that component says that how many vertices from outside of A can be added to this partitioning. So for example, if my set is A is ABC, these are the different states over ABC. I can either put each of them into one partition and say that I'm not going to add anything to this partition from outside of A, or do the same thing and say that I'm going to add something here, and so on. And then I say that a partitioning of the graph realizes a state if they don't contradict. That's very easy. And I say that two states are compatible if there is a single partitioning that realizes both of them. So basically, two states are compatible if you can glue them over each other and get a state for the larger set. And here's the algorithm. What I do is that for every node T of my tree, I define several variables that I'm going to compute in a bottom-up fashion. And at first, I initialize them to, let's say, infinity. And the invariant that I want to satisfy is that after I compute dp of t and s, and okay, t is the node here, and s is a state over the set of active vertices, red vertices in that node. And I define the dp of t and s as the minimum total weight of cross edges over this graph. So instead of looking at the complete graph, I only look at this partial graph, and instead of looking at all the p partitionings, I only look at p partitionings that realize this given state S over the red vertices. And doing this, it's easy to see that you can compute these values recursively in a bottom-up fashion. And these are the formulas that are all easy to compute, but I'm not going to go through every one of them. I'm just going to go through one or two. So consider this case. Let's say that we have a node T in our tree that introduces a new edge. So if I want to find dp of T and S, S already gives me a partitioning over all the red vertices, and the red vertices in T and T1 are the same. So I can take the same partitioning and just look to see if this new edge is a cross edge or not. And if it's a cross edge, I add its weight to my total answer. Similarly, for join nodes, I have a graph, and I know the partitioning on the red vertices. Here, it's just one vertex. So I can use the same partitioning in both of its children. And also the graphs have no other common factor other than the red vertices, so I can easily just sum them up. So I hope I have convinced you that I can compute all these dp values in linear time. And now the final point is that when I want to find the total weight of the best p partitioning, I just look at my root. Here the graph is the entire graph, and I know that at least one of the states over the root is going to satisfy my best p partitioning. So I just take the minimum dp over everything that I have computed at the root, and this is my answer. So we have this theorem that if the access graph has constant tree widths, then data packing can be solved in linear time. And going back to this picture, the way we extend this theorem to larger cache sizes is that we say if the access hypergraph of order m-1 p plus 2 has constant tree widths, then data packing can be solved in linear time. And we also have a proof that m-1 p plus 2 is the optimal value. Like anything less than that will give us NP hardness. Finally, I just want to justify that this thing makes sense. We implemented a lot of different common algorithms, like basically everything in the book CLRS. And we computed the access sequences of these algorithms and their tree widths for access graphs and access hypergraphs. And we realized that when the underlying data structure of the algorithm is a list or an array or a tree, the tree widths increase at first, but then they stabilize at a constant. But if the underlying data structure is something weird, like in computational geometry, then they don't. So here I have a counterexample where they just keep going up. So basically our algorithm is mostly applicable to cases where you have trees or arrays as the underlying data structure. And here's a comparison of the number of cache misses that our algorithm leads to. We are the blue one, and it's the optimal number, versus several different heuristics that we checked. And in almost all cases, the heuristics are off by between 15 to 30%. So in conclusion, we showed that data packing can sometimes be solved in linear time. We showed that it's actually harder than what we knew before, so we have new hardness of approximation results. And I'm ready to answer any questions that you might have, and I'm going to put this one up because I expect this one is the thing that is going to have more questions. Okay.
Okay, who has a question? Please.
Can you say something about the sizes of the constants that are involved in your linear time algorithm?
Oh, the constants depend exponentially on the size of the cache, so on M and also exponentially on P. So this only works if the cache is pretty small. But if you look at the hardness results at the very first here, even for very small caches, it's hard to approximate an NP hard in general. So at least we can solve the small cases.
Other questions? I have a quick question. So you have a nice diagram at the end that shows that you've kind of spanned the space of questions that you might ask along these dimensions. Are there other questions that you haven't answered that you're interested in?
Well, one thing that we're interested in is to look at what happens if you have different levels of cache. Right now, you just have one level. And it seems that things get much more complicated then.
Okay, thank you.
Thanks.